Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed discrete time modeling, and in this present lecture, we will start about this continuous time models. So, in the discrete time models, especially we have dealt like finite difference methods, that is especially called difference methods we have used. And we will just discuss about what is the discrepancies or the disadvantages we have just to find in the discrete time models, and how we are just approaching towards the continuous time models, that we will discuss in this lecture. So, first we will just go for how we can use the continuous time modeling, and then we will just go for the differential equations. So, there itself we have just gone for the difference equations only, and then we will moving towards the solution of differential equations, and how we can just represent this differential equation in a geometrical form, that we will also discuss here. So, first if you will just go for the continuous time modeling. So, if you will just see our previous lectures, we have discussed there and analyzed these discrete time models, and if you will observe in a natural sense, that is in natural phenomena, all of them are depending on the time continuously, since whenever a system starts it ends. So, continuously the system proceeds in a phase wise manner. So, if you will just consider like previous points, then we can just move one by one and proceed, and finally we can reach to the end points. So, then why did we use the discrete time models? That is also a question. So, there is a very close link between discrete time and continuous time models, since sometimes if the points are like placed in a finite difference forms, that is equispaced points if it is placed. So, it is useful, or it is very professional to use this discrete time levels to join it in a continuous form. So, that is why we are just saying here there is a very close link between discrete time and continuous time models. If sometimes you can just find that if the numerical methods is applicable, this means that the solution in analytical form, it is not possible there. So, already we have discussed that like linear equations or like quadratic equation, it is easy to get these solutions in analytical form, or exact solutions it can be possible. But if the point where this analytical solution will not be exist, then we will just go for this numerical methods. So, that is why, so we have just write the statement here as you are aware of using the numerical methods in the cases especially where finding the analytical solution is a cumbersome or impossible task. So, many of these industrial problems or like engineering problems, you can just find that there does not exist any exact solution of this differential equations or the difference equations. So, mostly people are using numerical methods to get the solution of this differential or difference equations. So, if we will just consider that where the discrete time models are being formulated, and if the data are given at discrete points, suppose like population levels, if you will just see in the population counting in India. So, usually like before 5 years people are predicting that this is the population level will be. This means that if suppose the population level is given at 1920, 1930, 1940, 1950, we are just predicting that this will be the population level in 1950 there. So, this is the projection analysis, especially it is used using this discrete points, and then also this discrete time modeling is done in that sense. So, in that sense, if you will just go for like further process, then we will just go for this continuous modeling. So, there are two important reasons to use discrete time models, especially if you will just see when data points are at finite distances. This means that we can just use this model when these points are like equidistanced. This means that suppose the point is starting at x0, then x1, then x2, x3, x4, and all of placed at the equal distances. Then especially we can just denote like xi as xi minus 1 plus h, or we can just write as xi equals to x0 plus ih there. So, in that sense if you will just see, we can relate each of the points make it, or the process can be described in a like continuous phase there. So, second point is to solve the differential equations. So, to solve the differential equations, usually many different schemes it is used there, where all the points should be placed at equidistanced. Neither we cannot use this equidistance level or finite difference schemes. So, the question is now that are discrete time models not able to show the actual behavior of the system? Especially the answer is exactly no, since discrete time models have their own limitations. Since if you will just consider like 3 different points which are just placed at equidistanced, but if the question is asked to find any in between any points the values of that functions. So, if you will just use, maybe there is existing a error between these 2 points. So, whenever we are just approximating the functions with the straight line here, then definitely we can just find a gap between this straight line and this function there over. So, at that point you have to choose your limitation that the error should be minimized there. So, the major advantage of using these difference equations is the dilemma of choosing the type or order of a difference equation. It is a matter of accuracy. When any differential equation is discretized to form a difference equation, as I have explained here. So, if you will just approximate any function with a straight line, suppose at different points, we can just find that if the points are suppose in a equidistanced, then we can just find there exists a gap between these 2 points here. And especially if you will just choose these discretized points also very close to each other, then this error or the difference between this function and this straight line, it will be minimized, but the error will exist there. This may cause like if it is a like large scale problem, it may cause a huge problem there, since small errors it will be added and it will just create a big problem there. Especially a practical example, if you will just consider like if a small error is introduced in a like a ISRO system, suppose 100 scientists are working. So, then this small error first introduced by 1 people there, then this error will be propagated to the 100 people there. So, this error will be like increased in the exponential way, since in each of these phases you can just find the error will introduce and this error will get in increase. So, that is why we are just saying that discrete time models have their own limitations. And if we will just go for accuracy level, especially we are just finding that this difference between this straight line and this like curve or the function, it is just existing. So, always we will just go for how much accuracy it is just providing the solution for us. So, for that if you will just consider like any differential equation is discretized to form a difference equation, then exactly we have to care about the accuracy. And the accuracy of a solution generally increases with the increase in the order of the difference equation, but we must take care of the computational cost. Since if we will just introduce this error, to minimize this one we have to go for like several iterations, or we have to use like several sub routines to minimize this error there. So, it will have like a huge human cost it is required, or it will take a long time to get the accuracy of this class of solutions. So, if you will just go for this like to overcome these limitations of discrete time models, we need an evolution in formulation of a model. So, our earlier approaches, if you will just see, was to make a suitable model which satisfy the data and the law governing this data. This means that whatever this data points it will be just achieved there, it should satisfy the system there itself, or the natural law whatever it has been satisfied by the system, it should be satisfied there. So, after solving this model, we can obtain an expression representing all the data in a sequential manner. So, first we will just formulate a mathematical model, then we will just generate the data, and this data should satisfy the natural law whatever it is satisfied by this system, and then we can just put this data in a sequence manner to represent it in a complete phase. So, to find a model in a proper equation form representing all the data sets in a continuous mode. So, if it is not in continuous mode, then we cannot distinguish that how the system is behaving like as time proceeds. So, that is why we require these continuous time models. with classical approach especially, deterministic continuous time dynamic systems are formulated by using ordinary differential equations or partial differential equations. So, especially if you will just see any natural system, there involves the differential equation terms or the partial differential equation term, since one of this variable it gets changed according to the other variable there. Suppose if you are running, playing, or you are purchasing something, so according to that you can just say that one variable gets changed according to the other variable, and this change is occurring at different levels. So, these different levels we are just setting as points there. Like if the system is get changed like at equal intervals there, then we can just use this discrete time modeling, and if you just join all these points in a like sequence form, then we will have a continuous model there. Or this time modeling we can just use that as time proceeds, then we can just establish this relationship with each of the points in a continuous phase, that as time proceeds or as one of this variable dependent on other. And that is why depending on that we can just say that it can just formulate a relationship between a dependent variable with a independent variable in a complete sense. And if it involves, then we can just say it is a differential equation or a partial differential equation. So, if we will just go for this introduction to the differential equations, an equation is called as a differential equation if it involves differential operators. So, especially this differential operators is denoted as capital D, which is represented either d by dt, d by dx or d by dy. So, any of these variables we can just involve here to get the equation as in differential form. But this capital D is always denoted as a differential operator, and d by d of some factors which can be expressed as the capital D. And secondly, a differential equation is termed as an ordinary differential equation or especially called as ODE if there is only one independent variable involved in that equation and rest all are dependent variables. So, just if you will just see here, like suppose a equation which can be written as a dy by dx, since you are just writing d is the operator here which is operated on y, which can be written as a d by y by dx here, and which can be written as suppose y here, or we can just write dy by dx equals to x suppose. Then we can just say it is a ordinary differential equation, since we will have one dependent variable here and one independent variable here. And especially this is called ordinary differential equation if there is only one independent variable. If you just see here, so x is the independent variable and y is the dependent variable here, and here also the same thing, y is the dependent variable, x is the independent variable. So, in a continuous phase if you will just write this one, then we can just write this one as a dx by dt plus dy by dt, this equals to suppose 1 here. If you will just see here, this dependent variable is like x here, y here, but the independent variable if you will just see here, only t is there, the independent variable. And if there are more than one independent variables involved in a differential equation, then we can just say it is a partial differential equation. More than one independent variable means you can just say that suppose a partial differential equation is written as del y by del t plus del y by del x equals to 1 here. If you will just see here, t and x both are independent variables and the dependent variables are like y here. So, that is why it is called a partial differential equation. And especially if you will just see here, for this ordinary differential equation, dx by dt plus dy by dt equals to 1 has only one independent variable t, while x is represented as x of t and y is represented as y of t are independent variables. Since t is independent, so x must be dependent on t to get a change with respect to t there. Similarly, if you will just see here, t is independent variable and y will get change with respect to t there. That is why y is called the dependent variable and t is the independent variable. So, similarly, here also in the partial differential equation, if you will just see here, del y by del t plus del y by del x equals to 1 here has two independent variables t and x, while only one dependent variable y, which will get changed with respect to t, also with respect to x here. Since t and x are like independent variable, they will not get changed, but this y factor that will get changed with respect to t, also y will get changed with respect to x there. So, that is why we are just writing here only one dependent variable y, which is dependent on t and x both. Hence, it is a partial differential equation. So, next we will just go for order of the differential equation. This is a very important aspect to solve the differential equations. The order of a differential equation is the order of the highest derivative involved in it, and the degree of a differential equation is the degree of the highest derivative appearing on it. So, degree should be considered for highest order differential operators only. So, sometimes people are get confused that what is the, since if you suppose some of the terms that have involved like highest order and some have involved like lowest order but highest degrees. So, they are got confused that what is the order and degree of that differential equation. So, you have to keep it in your mind that degree should be considered for a highest order differential operator only. So, the operator which has the highest order, the degree can be considered for that term only for the complete differential equation. And after the equation is expressed in a form free from radicals and fractions as far as possible. So, if some fractional numbers are there, so it is difficult to say what is the order or degree of that differential equation. And degree is always a whole number, it cannot be a fractional number, but order may be fractional, since nowadays people are using like a homotopy analysis method or homotopy perturbation method or any like differential transformation method. So, this involves the differential equations with fraction order are termed as fractional order difference equations or differential equations. Especially for this we have just considered certain examples here, that is x dx by dt, this equals to dx by dt whole square. If you will just see here, it is a first order and second degree ODE here. Since if you will just see the order of this differential equation term is 1 here, and order of this one equation is of 2 here. But if you will just see here, it is called to be first order and second degree. Degree means if you will just see here, the degree is a 2 here and order is a 1 here, 1 here. So, that is why we are just saying that this will take the highest degree, the term involved as of highest order here. So, that is why this is called first order and second degree ODE here. And if you will just go for like a calculation of the order and a degree of this differential term here or the differential equation here, then it is of second order and second degree ODE here. So, it can be like as we have discussed here, degree is always a whole number, and first we have to make this as a radical free. So, that is why if you will just made a square of like numerator and denominator, we can just find this one as like square here, and this will be like a whole cube here. So, which can be radical free, and we can just say that since it is of second order and second degree term is present there. So, that is why it is called second order and second degree of ODE. So, then we will just go for like a differential equation is termed as a linear if the degree of each differential equation or degree of each differential operator is 1 and no two operators are multiplied together or with a dependent variable. So, especially we can just write this basic definition of linearity is that the degree should be always 1 there, and no product of a dependent variable and derivative should be present there. And sometimes the differential equation is called nonlinear if it is a nonlinear differential equation, that means the degree should be 1 and it should be free from the product of dependent variable and derivatives. Then we can just say that it is a linear equation. So, to like explain these factors, if you will just write a differential equation as x dx by dt, this equals to dx by dt whole square. So, if you will just see here, x is multiplied with dx by dt term here, and also the degree of this dx by dt term, it is 2 there. So, that is why we can just say that it is a nonlinear equation. But if you will just see here, dx by dt equals to x here. So, its degree is 1 here, and x power x is not multiplied with any of the factors. So, that is why it is called a linear equation. And if you just see this third equation here, d square y by dx square plus dy by dx whole cube plus y equals to 0. It is non-linear because the degree of this dy by dx term is 3 here. So, that is why it is a non-linear equation. So, further if you will just proceed for the solution of differential equations here, a solution of a differential equation is nothing but a relation between all the dependent and independent variables involved in the differential equation. This means that obviously whatever the solution it will just come, if we will just put in the differential equation, then it will just provide us a solution there, or it should be satisfied this differential equation there. So, especially whenever we are just obtaining the solution for any differential equation, we are just saying there is a general solution, there is a particular solution is existing for the differential equations. Why it is existing? That since whenever we are just approaching towards a solution of a differential equation, it always involves certain constants. And if the constant is involving there, then a generalized solution we can just obtain from this differential equation. So, that is why the basic definition of this general solution is that a general solution of a differential equation is that in which the number of arbitrary constants is equal to the order of the differential equations. That means, whatever this order of this differential equation, the same number of constants it will appear in the solution itself. So, particularly we can just say that a particular solution is existing for a differential equation, or a particular solution can be obtained from the general solution by giving particular values to the arbitrary constants. If some boundary condition is prescribed, or if we are using certain methods to find a particular solution from the general solution, then we can just get it by choosing this arbitrary constant values, or we can just determine this arbitrary constant values to get the particular solution. Since arbitrarily, if you will just see constants values can be changed according to the solution process. So, that is why we are just saying it is a particular solution there. This means that for the particular values of these constants, this solution will satisfy the differential equation. So, further if you will just go for like a differential equation may sometimes have an additional solution which cannot be obtained from general solution by assigning the particular values to arbitrary constant. This solution is called singular solution. Sometimes you can just find the regular solutions or singular solutions. If some dividend terms are multiplied there, where this analyticity preserves that point at that level, then if the dividend term is multiplied with the differential operator there, then we can just find this singular solution there. So, that is why we are just saying that sometimes the solution only exists, but an additional solution which can be added with the general solution there, but that can be obtained using the particular values to arbitrary constants, and this is especially called singular solution. And if you will just go for like geometrical aspects of this solution of a differential equation. So, we have just considered one simple example here, that is solve the differential equation, suppose dy by dx equals to x here. So, if you just integrate this dy term, and if you will just multiply here dx term in the right hand side, then we can just find the solution as y as x square by 2 plus a constant there. And if you will just plot this solution, then we can just obtain the general solutions. If you will just see for different constant values, we will have like different curves here, and that is why a general solution will always have as many constants as the order of the differential equation, and the given differential equation is of first order. So, it has only one constant, and all the general solution differ only by constant terms. So, whatever these constant values you can just choose arbitrarily, the solution will like shift their positions according to that one. Since it is a linear equation only, so that is why we are just adding one constant, and this constant will shift the positions of this like nodes from one point to the other point, and the trend of the graph remains same. And if you will just go like if the curve of the solution like y equals to x square by 2 plus constant is passing through a particular point, say suppose 0 0 here, then the value of a constant is turned out to be 0 there. So, whatever this constant values it will just give you, or it has been provided. So, accordingly this point will just getting a shipment with the axis. Hence, y equals to x square by 2 is the particular solution of the differential equation. Since particularly we are just assigning one value c equals to 0 there. So, that is why we are obtaining this graph there. So, that is why it is called a particular solution. And for constant of different values, this means that different constant values if you just provide, we will have different like shipments of the graph. So, if you just go like for any particular differential equation of first order and first degree, the generalized representation of this equation is like dy by dx equals to f of xy. Suppose the solution of this equation is given as g of xy equals to 0. Since obviously you can just dy terms can be separated, or it can be taken the y terms to the left hand side and x terms it can be separated to the right hand side, then we can just obtain a solution by using different methods. So, that we will discuss in the next lecture. And the solution, especially since this differential equation involves x and y terms both. So, that is why the solution will also includes both the variables there, x and y. And if we take any arbitrary point, suppose p of x0 y0 satisfying g of x0 y0, this equals to 0, then the point will also satisfy corresponding differential equation and vice versa. And especially if you will just see here, the term dy by dx in the differential equation will give the slope or tangent of the curve g of xy equals to 0 at the point P. And all such curves, if you will just see here, the tangents are existing at these points, if you will just see here. And all such curves which satisfy g of xy equals to 0, since g of xy it is just satisfied, or it is represented in this curves here as referred as family of curves represents general solution. Accordingly, we have just shown that shipment can occur according to the constant values, and at each of these points we can have a slope which is nothing but the representation of a dy by dx term there. And the curve g of x0 y0 equals to 0 is a particular solution to the differential equation that we have explained in the previous slide. So, this is the geometrical representation of this differential equation. Sometimes people are also representing this tangent planes or tangent lines according to this differential operators. And furthermore also you can just find that manifolds and some other factors it can be associated with these differential terms. So, from this lecture we have just find that the advantages and disadvantages of the discrete time models, and then we have discussed about continuous time models, how we are just representing these continuous time models in different forms. Then we have discussed about conversion of a differential to differential equation if it is equispaced points are present. Then if equispaced points are there when we are just approximating a function with a like a line or some other factors, then exactly if the straight line is satisfying the exact solutions, then this curve is differing at many points which will not provide a accurate solution. So, that is why accuracy and computational cost we have to see when we are just applying this difference method for the differential equations. Then we have introduced the classification of like ordinary differential equation, linearity, non-linearity for this ODEs, and then type of solutions of ODE, and whatever the representation for the differential equation in a geometrical form. Thank you for listening this lecture.